folks. It's been a long day, but I want to try something else. Today we are going to talk about networking, and while the concept and all the knowledge is immense, so you could spend years studying it, I believe that there are a few key concepts you can learn very fast, which will be enough to start working, troubleshooting, and setting up networks. Today, imagine this like a dummy video, but I will touch on some useful tools and concepts, and theoretically, if you understand what's in this video, you can already start working in the area. So on the screen you can see this picture of different networks, cloud settings, servers, and it seems greatly complicated. But in reality, in the background there are just a few concepts that you need to know to fix or find the problem of a network connection. It goes without saying that you should look up and try to learn OSI model or TCP IP model. Let's just go briefly through that. So on the bottom layer there is a physical layer. So there are real cables which carry real electrical signals. Usually these are called like patch cord, and there are multiple signals traveling through multiple cables, and there is a lot of physics behind that. Basically one of the signal is let's say a power, so it's either higher or lower voltage, and it gives you 1 or 0, and another cable shows you the frequency which you need to measure the voltage with. So basically you look at the clock, you look at the voltage, and you get the signal 1001. That's in brief how it works. So it's a lot of data going through the network from multiple cables, right? However, the data cannot be endless. It must be discrete. We must be sending data in some controllable sizes. So if you remember my video about disk, there was a concept of clusters and data blocks. In network, there is a concept of frames. So the data is sent by frames, and the frames have a limited size. If you check the properties of your network card, you'll find a setting called maximum transmission unit, MTU. And you can make it higher or lower, which will depend basically on your network requirements. You can have to send many small frames if you know that there are network interruptions, so you would retransmit faster. Or you could send bigger frames, which would probably work better, but your devices on the way must support the size. And typically if you have size set too low, the frame will be very fragmented as well. So there are a lot of different ideas. Just know that by default, the frames do not go above 1500 size, and if it's above, it's called jumbo frame. So you need to have devices on the network which support jumbo frames. Then within the frames, the data is sent in packets. So the packet is the actual payload, which has a header which explains what kind of packet it is, and inside you have data, and you have a concept of encapsulation. So for example, in the IP packet with the IP header, you'll have TCP information, TCP packet. So you kind of have like an envelope which goes to your apartment, like IP address, and then you have TCP port inside which goes to specific person in your apartment. I'll elaborate this shortly. And then it goes to the layer of sessions, because you may have multiple connections happening at the same time, and then it gets sent basically to applications to decrypt, to encrypt, and to process data. So this model can be summarized pretty briefly. There is more behind this, and TCP model is similar, but it kind of makes an easier picture. So instead of 4, I think you have 2 layers on the top, but otherwise it's more or less the same. But that's not why I'm here. Today I want to show you how two computers would actually communicate, and what can you do to troubleshoot connectivity, including some specific tools and command line utilities. So let's say you have 2 computers and you want to send a picture from one computer to another. And today I'm going to try to use a tablet. So I'll be drawing some things. Hopefully it's not going to be too ugly, but we'll see how it goes. Let me check my brush size. Okay, let's go. It's too big, I guess. Yeah, that should be nice. So you will actually have to connect the computers somehow. So this is the typical cable you can see on the screen. It's called RJ45. the type of the connection. People call it patch cord, and there are other names for it. But this is a typical network cable which you would use for local connections, for connections to the devices like switches and routers, and to the connections which go outside. So this cable will be plugged in somewhere. So obviously it will have to go like this and go to another computer, right? And there are like two small red and yellow lights, so they turn on when you plug in the cable, which means that the cable is connected successfully, and they'll blink once the data is being exchanged. So if you connect computers like this directly, you can already start communicating. But typically there are devices on the way, for example switches and routers. I'm not going to elaborate too much in this, but the main difference, you can imagine that switch is something that is connecting many devices in a single network, so you would basically have many cables, but it's a single network. And the router is a device which will allow you to connect multiple networks together, like one LAN to another. LAN is local area network, it's a single network of computers. And typically routers include switching functionality, and newer switches that are sold on the market also include routing functionality. So the line is kind of blurred. So you used to have hubs in the past. It's like a very old device which is just used to retransmit data. Then switches were introduced, and of course routers were quite old. And now switch and router are usually the same device in your company. So you buy like D-Link or Cisco networking device which will allow you to connect. Also on a router, sometimes one of the interfaces is marked with a specific like different color. For example, it can be like yellow or red around it, right? And if one of the holes where you plug the cable has a different outline, usually it's an Ethernet pipe. Basically, it's the connection which will be used to connect to your public network. So it will be going from the outside. If you connect your computer like from the network to it, it will not be on your network. You are supposed to plug the cable which comes from your internet service provider or from other devices you have in the network. And thinking about the internet service provider, there is no magical cloud where your data goes. It's just a bunch of routers and hubs and switches which retransmit your signal, and it goes through the city, to another country, underwater, in the ground, but all of that, most of that is in the cables. So how does the data go? Let's see. So let's say you are sending data, right? So it needs to go to your router. The date will be binary, 1001, etc. So it will be bits and bytes. 8 bits will become a byte. So as we just recognized on a picture about OSI, multiple bytes would make a frame. So there will be a frame traveling the network, right? And this frame can have a limited size which you configure as MTU. Now within the frame you'll have packets. So we'll be mostly focusing today on the packet delivery. For example, when you do ping, you send specific type of packet called ICMP. It is a specific protocol which needs to go to another computer and come back. And if it comes back successfully, you ping the device. If it doesn't, you get connection timeout. So when you send the packet needs to somehow find the target, right? So let's talk about IP packet, right? There's IP packet going out, and this IP packet needs to know where it's going. So the computer must have some kind of identifier. The typical identifier used right now is called IPv4 address. Why v4? Because there's also v6, but it is not as popular. And it looks like number dot number dot number dot number. For example, 192.168.0.10, right? This is IP address. So another computer would be also with IP, but it will be different IP address. So you would normally never have similar IP address in the same network, otherwise it would be a conflict. So here we will have 192.168.0.15. So the packet would have that goes to the address 192.168.0.15, right? This is the target IP address in the packet. And of course, if you want to be able to reply to it, the target computer must know where it comes from. So there will be a source IP address 192.168.0.10. So these are basically the most important parts of the IP packet, which are used to address the packet properly. So when the packet comes to the router will find another connection that is assigned to this IP address and send the packet there. Let me use a different color. So now it's retransmitted by the router. It goes to the other computer. And these holes where you plug the cables are called Ethernet ports, but these are physical ports, Ethernet ports. Do not confuse them with TCP ports or UDP ports. So the port can be used in different places as a term. Right now, not to confuse anybody, we are just talking about IP addresses. So if you are pinging a computer, you are sending packet which contains target IP and source IP, and the packet goes to another computer. The computer network card receives it. The operating system with network drivers and everything acknowledges it and sends it back. So now it starts to go back. And now it will reverse the source and target IP, because it is going to 192.168.0.10, and it's going from 192.168.0.15, right? So, and this is how the router, when it receives it on the same cable, it's going to be able to retransmit it back to the original computer. So this is the basic concept of how the IP address is used, right? So that should be enough for general understanding. Now, there is a specific property called subnet mask. So let me explain why we have it and what is the use case, like why do we need it. So at first, let's quickly check how can we find out which IP address does our computer have. I will use command line for that. So there is a command called ipconfig, and if you add ipconfig/all, it will display all network adapters you have. And in this case, I can find my IP address, which is here, 168.152, and there is a subnet mask. So what is a subnet mask? Briefly, it is a binary, let's say, borders. It tells how many IP addresses do you have in your network, because you may want to use a specific number of computers in the network, and you may want to isolate this network from other computers. So you want to plan a network which only has 10 computers. So you'll need at least 10 IP addresses. So you will use a mask which allows you to have 10 IP addresses, and basically it's a bit of a math. You apply the mask to IP address. Like for example, if you have IP address 192.168.0.15, right? And then you have subnet mask 255.255.255.0. It tells you that 255 is busy, right? So this is your network. And whatever is not busy, by basically not blocked, this is where you can have your address. And the maximum number here is 255, which means that this is how many different IPs can be within the network. If you would put something else, for example, you would convert this to a different network, you could have more or less address space for your IP address of the computer. Typically, it is possible to calculate it in your head, but I usually use network calculator. I don't set up networks often. If you do it often, you would remember how to calculate it fast. But the only thing you need to carry out right now is that subnet mask is basically telling you how many IPs do you have in your network right now. So this is something to set up on the network layer. So the computer would define if the IP address, let's say 253 in the end, if it would be part of your network or not, and then it would decide if it can route there or if it can not send data there, because there is not such IP. So it's just a limit. You have a starting IP, let's say 0.1, and then you go up to the amount which is allowed by the subnet mask. And one more thing that you will notice in the IP config output is that there is a default gateway. This is the IP which is used as a router. Basically, this is where the request will go to get out of your network. This is especially important if you need to communicate through multiple networks, because you could broadcast, which means send address to everybody in your local network, but this signal wouldn't go to another network. So you would have to send, let's say, ping to computer from another network to gateway first, and then the gateway, your router would send it further to another network which is connected. So this is the IP which tells your network card what would be the destination of a specific request which needs to go to the different IP address, not in the same subnet. So ipconfig is a basic command which you can probably run many times. You can check if the settings are correct. For example, if you have two computers on the same network, they would have the same subnet mask, and they would have the same, not the host, but network address part. So if you have this mask, two computers which have three first numbers the same would be in the same subnet. Of course, they still have to be physically connected, right? Because what you can do, you can make two networks with two routers with the same settings, and by running ipconfig, you would be unable to determine if it's the same network or two different networks, because settings would be the same. What you could do, you could check MAC addresses of your devices. For example, there is a physical address which is unique to my network card. So on this card here, on my computer, I have MAC 1, right? And this is an address which looks like GUID, something we discussed in Hyper-V training. It's a bit different from GUID, but it's kind of unique still. It's hard to have the same address twice if all of these numbers are randomized from 0 to 9 and from A to F. And then on another computer you have MAC 2. And because the MAC addresses are different, you wouldn't normally have multiple networks which have the same device with the same MAC addresses. So if you are not sure if you are connected to the same router or to two different routers, right? Let's say you don't know if it's two routers. You can simply check MAC addresses of other devices in a network. For that, the command is ARP. It's the same as a protocol which is normally used to understand what is IP of a computer based on MAC. So ARP-A would show you other addresses you have in a network. In this case, I have my router, which is 101, and it shows me the MAC address of my router. So if I would run this command on another computer at home, I would see the same IP with the same MAC, so I would know that it's physically the same network. All right. Now, getting that out of the way, does it mean that if you don't ping a computer, like if the ping doesn't work, does it mean that you are not in the same network or the network is not established? Not really. As I quickly mentioned, pinging provides basically reply based on the answer from another computer. And another computer may have a specific software. There is a software which even comes with Windows, which is called firewall. And the firewall can theoretically block any type of connection you configure. So if you block ICMP traffic, your ping request would get to the router, it would get to another computer, but because ICMP is blocked, you wouldn't get a reply. However, you could block ICMP only and work through other protocols. So even if the ping is blocked, which could be blocked due to security reasons, so nobody would check which IP addresses do you have in the environment, you could still communicate with other programs. So it is not an indication that your network doesn't work. So the ping is a useful tool, but it's not a guarantee that the network works or doesn't work. And also you could theoretically allow ICMP and block everything else. So the ping would work, but nothing else would work. And I'll expand a bit on what you should check if you want to test connectivity for specific software. So let's go. So an interesting question. Let's say you are connecting with remote desktop, RDP, right? And you also connect with, let's say, with SSH. Maybe you have SSH client on another computer, right? So let's say you have two connections. I'm going to omit router, but let's say they're going through the router, right? You have one connection through RDP, and you have another connection through SSH. And the main question is, you have a packet here, right? And you have a packet here. And they both have the same source and target IP, because they come from the same network card to the same network card. So how would you understand if the payload is for RDP session or for SSH session? This is where understanding OSI model is kind of important. If you have different sessions, which means different applications communicating, the only way to understand the difference between their packets is to provide another identifier. So while your computer has its own IP, right? Something that is critical to know for general communication. It's not enough to establish multiple connections between different applications. So this is where the other protocol, the transport layer protocol, comes in. So typically most of applications communicate with TCP or maybe UDP. So in case of RDP and SSH, you can consider these connections like TCP connections. What does it mean? It means that you provide another packet, smaller header basically, inside of your IP packet, which will tell you extra information about TCP. And this information will mention source and target port. So on the target here, you will have an RDP port. Right? So you are actually connecting with RDP client, this client, to RDP server. And you're connecting with SSH client to SSH server. So you are not connecting to nothing. There is a program running on another computer which accepts your connection. And RDP server will have port 3389, if I'm not mistaken. And SSH will have port 22 unless you change it. So the extra information that comes with TCP is called port number. And don't confuse it with the physical ports on the router. No, this is a TCP port. And because the packet contains the port inside, when you receive the packet on another end, by looking at the port, you know if it comes from RDP or if it comes from SSH. If it comes to RDP, if it comes to SSH. And this is, the firewall can also work wonders or sabotage your setup. You can have a firewall, it can block RDP port, but it can allow SSH port. In that case, one application would work, another wouldn't. So this is why the first thing you do if your application doesn't work while the ping does, for example, you always check if the port is blocked by the firewall. If it is, then, well, you have to open it somehow. The trouble is that the port can be blocked on another application. For example, on the router, you can have a filtering software which blocks all connections through the port 22 or for the RDP port. You could also have internet service provider devices which you don't have access to if you communicate between different locations. So there is a chance the port will be blocked for good and specific communication wouldn't work at all unless you establish a VPN tunnel. VPN is basically your own way to encrypt traffic in its own channel, and then you have control over settings so it doesn't get listened by intermediate devices. But right now we are talking about standard connectivity. So one more problem that could be happening is that besides the firewall, maybe the target service is not enabled, like RDP is not enabled, or it's not running, and then there is no port on the other end which would accept your connection. So you would go to the proper port, it would go through the firewall, but it wouldn't actually get a reply because there is nothing running. So after you check the firewall, before you start going crazy with the network, check Netstat. Netstat, if you do Netstat with parameters bona, and of course I have to run as administrator, I apologize, run as administrator, here we go. Netstat bona will show you the application and the port and if it's listening or not. For example, here I have what do I have? Chrome, which is already established. So this is not something that I'm interested in. This is right now a session which is going on. It's working. But there will be an application like NV container. Hold on, this one, NV container, which is listening on port 65001. And this is from my NVIDIA network card for updates. So now if something would try to connect to port 65001, it would reach my NV container application. And when you read these Netstat, make sure that you are reading it like IP port application. So the application name is below the port. So for example, this is the port and this is the application below it, svhost.exe. And this way you can clearly see that it's not something above, because I have made this mistake a few times where I read the whole name of the application above and I checked the wrong port. So in this case, you would check that you have your remote desktop application server running and it's listening on the port like this. You can also do Netstat into a text file, which makes it much easier to check the output. So the way you do it, you run normal command like you would do always, netstat -a, but you would, sorry, bonnet, but you would also use redirect symbol like this triangle bracket and output txt file, right? And this way you have the contents of the output in your text file, which you can search much easier. All right. Now, the other question is, if you check that the port is actually listening by the application and the firewall is not blocking, but the connection still doesn't work, you can assume that it could be an issue in the network in between. And the way you can prove it is by trying to connect the port. So you cannot use the standard ping application. I think there is PS ping and some Cisco ping types which can ping a port, but by default normal ping is a CMP, so it can't ping the port. I normally use a tool called, let me check, it's a tool called PortQRY. It looks like this. So if you open PortQRY, you can specify target IP like 192.168.0.15 and the port. And I would use Telnet for the connectivity because Telnet doesn't care what you connect to. It will either connect or fail. So now I'm clicking open, and right now it's going to throw me a timeout error after a while because there is nothing listening on that side. Let me double check it. So if I ping 192.168.0.15, yeah, pardon, it should be 192. Yeah, there is no reply. It's going to wait a long time, and then yeah, now it connection timed out. It would connect if the connection would be possible, the port was open. A very useful tool if you don't want to mess with the telnet, it's from Microsoft. It's called PortQRY. PortQRY UI. Here it is. It's on the Microsoft site. PortQRY UI. And this tool can give you a graphical interface to actually check a connection. It's very small, it's very simple. You don't have to actually do much about it. Let me check what I have just downloaded. It should be my PortQRY UI here. So this is what it looks like. So now you can specify the computer, 192.168, for example, 0. What's my, no, it was 100. What was my IP? I forgot already. 152. And now I can specify the port. Let's say, what was the port? 65,001, which was listening. Well, at the moment it's not listening for some reason. But what's important, it doesn't say filtered, because if the port would be blocked, it would say filtered here. And so I have checked, I have a port for my Steam program, 27,036, so let's check that one. And now you can see that it's listening. So there is a program running on this port which is ready to accept the connection. One more port you may be interested in is port 135. Quite a few operating systems, and especially Windows, like to use the concept of dynamic ports. So ports which are randomly created and assigned on demand. So in Windows there is a service called RPC Endpoint Mapper. You can see here in the big bottom RPC Endpoint Mapper query response. And when any application which needs a special port, like separate port but not predefined one, comes with this port, it will be given, let's say, one of the big port numbers, like 63,000. The ports go up to 65,536. And if this port is blocked, RPC cannot work. For example, when you connect to another computer through event viewer, through some applications which come from Windows, a lot of connection types use the dynamic ports. Dynamic ports mean that there is no predefined number, it's always random, but it's the same port for the session until the connection is closed. And you can see the output of 125 is a bit different because it gives you endpoint mapper service response, which is actually something that you would normally use, like these big ports to establish a connection. Now, coming back to our picture, we have determined that, yep, cool, we have definitely ability to communicate through ports. But at first, what do we do if it doesn't work? You may actually find out where the connection problem happens and how it happens. Especially when it comes to TCP, just briefly, some applications also may use UDP, but UDP is something that is simply sending packets through and through, and it suspects that something on another end will get them, but there is no checking the packets. TCP is a protocol, and this is why it's commonly used, which always double checks that it has sent and received acknowledgement of the connection, and if it cannot send, it will resend again. It will basically do repeated action. It's called retransmit. Let me show you what happens when the connection doesn't work, right? So imagine that there is a real cable going like this, and the cable is broken, right? There is a physical error. Then the packet which is sent would try to reach the target computer, but it would get lost. It would never reach the target computer, it would never go back. Another option would be that there is a firewall on the router which actively blocks further transmits. So in the TCP packet there is a specific part of header called flag, and it is typically a 3-letter flag which marks the purpose of the packet. For example, when you establish the first connection, it's called TCP handshake. There is a packet which has SYN flag, synchronization. The target computer receiving this packet would say ACK, acknowledgement, and that would mean that the connection was established. If the connection with TCP is finishing, so it's everything is sent, everything received, the flag would be fin, finalized. And if there is an error sending data, right, there would be a response packet saying RST, connection reset. And moreover than that, if the packet is actually received but not sent further by the router, there would be acknowledgement of receiving, and there would also be a reset. So you couldn't determine if it's a physical reset or if it's an application of firewall reset. But how do you see these flags? So I will make a separate video on a tool called Wireshark, and there are other tools which are quite useful for troubleshooting purposes. But what you do, you typically set up a tool on the primary computer and on the destination computer. And what it does, it captures all the packets you send and receive, and then you can check which flags leave and which flags arrive. So if you do not see a packet arriving, you know it was interrupted. If you also get a reset back, you can see where the reset is coming from. You can see on which router device the connection has stopped. And this is how you can also find probably subsonic wall or other internet filters and the internet, what is it called? Intrusion prevention systems, IPS devices or IPS programs. So the only way to actually learn how to use Wireshark is to set it up and work with it at least once. The most important thing when you work with such programs is to set up a proper filters. So you would only want to specify the source and target IP addresses. So you would have the target would be 168.0.15, because this is where you are trying to get, and this way it will filter the other traffic. And you could say only TCP, and you could even say if it's SSH and port 22, you could only say that the target port is 22. So if you limit the capture options, you get less total data. It's much easier to read, otherwise you'd be overwhelmed. And in Wireshark itself, as I will show you in the other video, the errors, the resets, are colored with I think either black or red, I need to check that, but basically it's visible on the view that you can immediately notice connection errors. So what you would do, you would ping the computer if you want to check if it's responding on IP, but it's not guaranteed that it's going to work if ICMP is blocked. If you troubleshoot specific connectivity, you would check which port the application uses and verify on the target computer with Netstat that the port is listening, so the application is started on listening. You would try to telnet or PortQRY into the port to see if it's listening, not listening, or if it's filtered or blocked, because if PortQRY says filtered, it's a very useful tool, you saw it's very fast. You can immediately see that the port is actually blocked, and you can even provide a range of ports. So if you run this command, you can say everything from like 65,000 to 65,100, and to actually go and query all these ports. So this is a very useful tool that I like to use. Also, you would want to know that if the connectivity breaks, you can still have a chance to find where using tracing tools. You want to set them up on both ends to have full picture, and you would also want to configure proper filters, like what is a source target IP, what is a source target port, what is a source target protocol type. If you try to filter UDP traffic, it's harder because you don't get resets to find error. You have to probably set up listening software on the routers. Usually it's way above, let's say, a support engineer in many scenarios. It comes to local networking teams. And finally, when you troubleshoot networks, make sure that you actually know how the protocol works. For example, if you try to provide this TCP troubleshooting method to UDP, you wouldn't get any resets, so you wouldn't be able to capture. And when you do the capture, if you set up capture over time, the capture itself, the same as with Procmon, it can overflow your disk with data. You can capture too much. So there are a few tricks which you can look up in the network, but I'll also include them in the video, where you can only capture the headers, not the whole packets, because you don't need to know what's inside of the packet. You need to know what's in the header to see if it's delivered, acknowledged, or reset. And as a bonus to the video, I wanted to quickly explain to you how does actually internet provider send data to websites, and quickly explain NAT and PAT, net address translation and port address translation. So let's say you have a router. So internally, your computer tries to go to the Google website, right? And on the Google website, of course, you would have a public IP address, which is something that I didn't mention, but the computers in the internet start with specific numbers. For example, if you go and ping google.com, it has IP address which is not in my network, it's outside. And you can also trace it, do a trace route, which is a command which shows you which hops, tracert google.com. You'll see how your packet travels. If you troubleshoot networking, you can also basically see which device is on the way. These are different IP addresses which come from my provider, and at some point it will stop working because ICMP is most likely blocked somewhere for specific devices. Like for example, if you have these stars, usually it means there is a firewall there. Yeah, and then it keeps going. So using this command, you can see the network path of your connection. And of course, every time you talk to Google, you usually go to specific local, let's say, proxy, not to a single server because there are too many users. But let's say if you had one google.com, so you would want to go there and let's say you want to request pictures of cats, right? So you go to your router through the Ethernet cable. It goes outside to your provider and finally arrives to the google.com, right? But imagine you have another computer. So this one was looking for cats, but another computer is looking for dogs. So here we have IP2 and there we had IP1. Right, so between the computer and router, it's clear how the packet travels because it has source IP, IP1, right? And it has target, which is your router IP, because the router itself has an internal private IP, which is a gateway. So normally the gateway looks like 192.168.1.1 168, for example, 01, right? So this is the IP of the internal network. And the router would also want to have a public IP. Let's say it has 172 something something, like 001. Of course, it wouldn't be this, but let's say it's the public IP. So the router has two IP addresses: the one which looks in the internet for external communication, and the one which looks inside for internal communication. So within the network, the packets travel. Obviously, they come from source of the computer which sent them, right? And the target of them is the router internal IP. So we'll call it R1. So this is R1. Now, when it goes from router to Google, it's also clear. It goes from the router IP. So we go from R2 to Google IP, right? So the IP which is assigned to the Google web server. And then when it goes back, it starts traveling from Google IP to router IP. And now it's only a question of intermediate devices to actually send data properly. So you would have routing tables which say you go from this network to this network, and eventually the data will go through. So now in this setup, there is a bit of a problem. So let's say we had two requests happening, and then we got two replies, and the replies come back to router from Google, and these replies come from Google IP, right, to router public IP, RPIP. But how do we know which one is for cat request and which one is for dog request? Because both packets come with the same source IP, which is Google, and target IP, which is router, right? Because Google has no idea about your private network, about your computers inside. It wouldn't be able to know them, otherwise it would defeat the purpose of the network, subnet. So it's clearly not enough to get this packet back and simply read IP. And this is where the router goes deeper. And now it looks on the transport layer. And here we would have a dynamic port. So what actually happened? If we go back for a bit, once you send the data to router, it traveled using IP inside of the LAN. But when the first request got out, it left from a random port, 65,036, for example. And when the reply comes back, it comes back to the same port. So TCP port would be the same. And this is how we know that this is for cats, and another one, which is 65,037, would be for dogs. So there are multiple sessions using the same public IP, but they go through different ports. So there's one more technology which you can use, which most of you have heard to some extent. It's called port forwarding or port mapping. You could pick a port, let's say port 80, on the public interface and map it to internal IP port 80. And this is something that you basically manually control if you want to connect to the HTTP port on internal IP through the public IP. But by default, it uses random port assignment. It uses dynamic ports, which are assigned on the fly, because you don't know how many connections you need. And there are so theoretically it's a limited amount of ports, but it's a huge amount. You never have so many computers in the IP network to exhaust ports. So to summarize, there are two technologies in play here. First technology is called NAT, Network Address Translation. So you go from network 192, let me pick my pen. You go from network 192, which is between your router and your computer. So on the internal interface you have the same network. And then you go to network 172, which is external network. So this transition is called network address translation. It's caused by a system called NAT. So the router must have a rule which says you are allowed to go from this network to this network. If you weren't allowed, you would be unable to ping and access anything from outside network. But when it goes out, because you open multiple sessions, it starts using random ports here. So you got port 1, port 2, port 3, and now you know that if you have the connection from IP address 15, it goes through port 1. If you go from IP address 17, it goes through port 2, 21 port 3, and this is called PAT, port address translation. So typically routers communicate using two technologies, NAT and PAT. I just hear people talking about NAT a lot, but for some reason some people just ignore that PAT exists in the answers on the interviews which I conduct. That should be all about these basics. If you want me to elaborate specific concepts, because there is a lot of things still to discuss, I would be happy to, and you have probably used some tools. I would be happy to see in the comments which tools you prefer. Maybe you don't like PortQRY, maybe you use some other tools which are better in your regard. Maybe you don't like Wireshark, you use Fiddler or TCP dump or something else. And if there are any specific requests for tools to use, I would be happy also to help you figure out how they work. We can set them up in the lab and do it. So that should be it for today. I'm going to wrap up the video. You can scroll back. That's the benefit of a video. You can scroll back and review specific sections and ask questions if I wasn't clear enough. Otherwise, I wish you a great day. I'm going to take a rest. It's been a long day. And I'll see you in the next video. Bye bye.